Hello again, everyone. And today's lesson, we're going to be looking at the alkali metals. So there are success criteria on the screen for you now. We're going to be able to describe the reaction of the first three alkali metals with water and with oxygen. We're going to be able to write equations for reactions involving the alkali metals and to order and describe trends within the alkali metals. So what do we mean by the alkali metals? Well, we're looking at group 1. Lithium, sodium, potassium, rubidium, cesium, and francium. They're at the furthest left-hand side of the periodic table, and they all have one thing in common. That is that they have one electron in their outermost shell. That's what makes them reactive. The difference in reactivity we'll look at in a few moments' time. So, the first thing I'm going to ask you to do is make a copy of this table. Then we're going to watch a short video where we will see these three metals, lithium, sodium, and potassium, reacting with water. So you may want to pause this video now while you make a quick copy of this table. Now I'm going to move on and we're going to watch the video. And as you watch the video, fill in the details regarding the hardness, the appearance, the reaction with air, and the reaction with water of the alkali metals. When thinking about the hardness of the metal, watch and see how difficult it is for the person to cut the metal. The harder the metal, the more difficult it is to cut. So here we have lithium reacting with water. Look at the way that the lithium is moving around the water. Also look if you can see the shape of the metal. It's still an irregular shape like it was when it was cut. Now here's sodium going in. Again, look at the shape of the metal. It's no longer an irregular shape. It's become a ball as it moves around on the water's surface. And finally, potassium. Now we're going to test some of the water that the metals reacted in. We're going to use the universal indicator. There we go. Of course, it's green at the moment because it's neutral, and it's going to change color. There it is. It's got a dark purple. Checking against the chart, we can check and see what the pH of the liquid is now. So what you should have in your chart is something like the answers here. The bit you weren't easy to see, or wasn't easy to see in the video, is how the metal reacted with air. So I'm just going to concentrate on that column there. So we've got the reaction with lithium. The outside turns dark and dull. This is what it says in each case. What you will have noticed if you watch the video carefully is that the rate at which the lithium darkens is slower than the rate at which the sodium darkens, which is slower than the rate that the potassium darkens. So as we're moving our way down the group, the reactivity is increasing. So some questions here. How do the alkali metals react with water? They move vigorously they react vigorously, moving around the surface of the water. They may even ignite. Now, it wasn't shown in the video, but if you were to place a piece of filter paper in the water, particularly with sodium, the sodium would then be restrained, and rather than the energy being produced being turned into kinetic energy, the energy level would build up and the metal would light. And whereas we got a lilac-coloured flame with the potassium, we would get an orange-coloured flame with the sodium. The most reactive metal, hopefully that was clear to everybody, it's potassium. Name the gas released during these reactions. Well, let's think back to what we were doing before. Acid plus metal gives us salt plus hydrogen. Water here is acting like a sort of acid, and so the gas that's released in this reaction again is hydrogen. And hopefully, the next question you are shouting at your screen, squeaky pop. So the hydrogen will burn with a squeaky pop. As I've said to you before, that's what they're looking for. Everybody knows what you mean when you write the squeaky pop test. Now, what do we think will happen when rubidium is placed in water? Well, rubidium is the next one down in group 1. What we should be seeing as we're going down group 1, reactivity is getting greater. And so if we add rubidium, we would get a violent reaction. There would probably be enough energy to smash the trough. Not only would it burst into flames like the potassium did, but it would be a big boom and the glass trough could well be broken. What this tells us is what we've already alluded to, is that as we move down group 1, the reactivity gets greater. Where do we think the name alkali metals come from? Well, the clue to that is at the end of the video that we've just watched. What colour did the universal indicator go when we added it to the water the metal reacted in? Purple. Purple is for alkali. So it produces a hydroxide solution, which is an alkali. So if we have a look at the reaction, we can see that when we add lithium to water, we get lithium hydroxide and hydrogen. The symbols for that, very straightforward. Li plus H2O gives us LiOH plus hydrogen. We need to add 2's in because remember, hydrogen always travels as a diatomic molecule. So we need hydrogen here, we also need hydrogen here. So it's 2 Li plus 2 H2O gives us 2 LiOH plus H2. Now what are we going to add in here? Well, it's the same reaction, only with a different metal. So it's going to be sodium plus water gives sodium hydroxide and hydrogen. So it'd be 2 Na plus 2 H2O gives 2 NaOH plus H2. It shouldn't be a massive leap for you to see that the next equation is going to be exactly the same, just with a change of metal. So potassium plus water will give us potassium hydroxide plus hydrogen, and 2K plus 2H2O will give us 2KOH plus H2O. Can you complete the word and symbol equations for rubidium and francium? Again, it's going to be the same pattern. Rubidium plus water gives us rubidium hydroxide and hydrogen. 2Rb plus 2H2O gives us 2RbOH plus H2. And for francium, the same thing. Francium plus water gives us francium hydroxide plus hydrogen. 2Fr plus 2H2O gives us 2FrOH plus H2. And as I've mentioned to you before, the exam board like to play about down in this place. They know that you have been exposed to sodium, lithium, and potassium, but most people don't get to see anything with the rubidium. So they are quite likely to set a question in terms of rubidium. All you need to do is apply what you know. The pattern is there. As I've said to you many times before, our greatest friend in the world of chemistry is the periodic table. All those patterns that Mendeleev was able to set up for us are very, very important as we remember and look at the reactions of the different groups. So, what happened when the alkali metals were cut with a knife? This was much harder to see on the video, and you might want to go back and watch the video again to check out the answers we're going to get here. So how do the alkali metals look when they're first cut? Well, like all metals, they're shiny. What did you notice happening to the surface? Well, over time, the surfaces became duller or tarnished, is the fancy English word for that. What causes this? Well, there must be a reaction going on. The only thing that the metal could be reacting with is the oxygen in the air. So the final question is, why is it important that alkali metals are stored in oil? Well, what does oil do? It prevents the two substances reaching the metal that will cause it to tarnish, oxygen and water, and therefore the metals will not react. The equation for this reaction, like any other, metal plus oxygen gives a metal oxide. Lithium plus oxygen gives you lithium oxide. I'm sure on your own you can write down the equations for sodium and potassium with oxygen. Now, we've mentioned that the reactivity is going on as we go down the group is getting greater. Why is that? Well, they're all in group 1. And when we look at their electron configuration, we can see that in each case, there is 1 electron in the outside shell. But why is it then that it's getting more and more reactive as we go down? Well, what we can see differently is that there are more electrons in each element. So if we look at these diagrams, the distance between the nucleus and this 1 electron is getting greater because it's further and further away from the nucleus. It's the nucleus that's holding that electron in place. The positive charge of the nucleus is holding all the electrons in their orbitals. The further away it gets from the nucleus, the less hold the nucleus has on the electron. Therefore, it's easier for it to drop off. So that's why, as we go down group 1, the metals become more reactive. The electron is further and further away from the charge of the nucleus that's holding it on, and it's much easier for the metal to lose it. By the time we get to francium, it's almost impossible to isolate francium as an element, because it really, really does not want that electron. So a quick question, why is francium the most reactive? Because the atomic radius is the largest. The distance between the electron and the nucleus is the furthest, so it's so much easier to lose that electron. So what I would like you to do is, alongside this video, you have been sent the comprehension activity. So I want you to read the comprehension questions and answer the question. Read the passage and answer the questions that accompany it. There are also some exam style questions here at both bronze, silver, and gold level that you also need to complete.